All right, recording is rolling. It is Wednesday, August 13th. So, main thing today is going to be algebra questions. I have a whole PowerPoint slide here. What I did is I went through you guys' book and I flagged a bunch of word puzzles. So, math a lot of times can be really abstract, especially algebra. You got X's and Y's and equations, and what does this really mean? So, I found a bunch of practical applications for these, and we'll go through and just think about these. Right? Yeah, so puzzles you guys be solved throughout the year. All right, so here's how we're finishing up this week. Well, I'll get as far as I can to today, and then Thursday and Friday, I'm gonna have you guys construct an abacus. Now, my last class didn't know. Guys, what is an abacus?
I feel like it's a super old school calculator with those beads.
Yeah, exactly. Winner. Yeah, super old school calculator with beads. That's this right here. Yeah, you guys see I'm sliding these beads up and down? Oh, something like this? Like this? Huh. So, these could represent numbers. How can you count on this? How can you... Oh, okay, so have you guys construct this over the next couple days? I'll show you... well, by the weekend, you guys know how to add, multiply, and take square roots. Turns out just sliding beads up and down, you can take squares with these. Okay? So think about counting a little bit here. There's suppose like 100,000 years ago, people just like running around in the savannah. It's like, okay, well maybe they can count to like 10 or 20 or something. Oh, there's there's like 5 giraffe over there, right? But yeah, at some point you gotta have a system for this. Let's bring in like Roman numerals. So let's go back 2,000 years ago. So Romans using Roman numerals, right? Maybe they have to start counting seriously, like okay, how many people do we have like in this army squadron over here, or how many? Right? But Roman numerals, guys, are Roman numerals very good for doing high level math? No, because you can kind of count up to like a few thousand, and that's about it.
Yeah.
But if you want to do some serious math, some serious algebra and calculus and on, you need a place value system. Have a place value system, you need a concept of the number zero, right? So that's all fun. Do that. Okay. So guys, what base system do we use? We have a base what system? 10, base 10. So you memorize 10 different characters, 0 through 9, okay? And then it rolls over to the next place value, 10, right? But that wasn't the only place value system that was used. Here, I'm going to switch over and show you guys. So right before I switch over, almost missed this. Guys, planner. You guys have a planner? You guys are using planner? If you don't have a planner, then ask your parents for a planner and start using that. Because get much guys to have that. Let's see. I think I got yeah. Have this was back in the 1970s. There was got one of these early digital calculators, and then the Sorbonne abacus built into this too. Because yeah, again, like before the 1970s, it's like, well, how did people do calculations? Right? How did we actually run the Apollo program and land astronauts on the moon? I mean, they didn't have these nice digital handheld size calculators back when we were running the Apollo program and landing astronauts on the moon, right? You had an abacus, you had slide rules, that kind of thing. Got some cool pictures here. Let me find it. Sorry, the screen froze. Be doing this sometimes. Okay. Let's see what else I got. This one. No, right. There's actually 2 different versions here. This one on top is a base 16 abacus. Right. So there are different place value systems. This bottom one is the one I'm going to have you guys construct in class is actually a base 10, which is that's pretty standard worldwide, just use base 10. But if you look over history, there are different place value systems that actually have developed, like base 8, base 12, those are popular. Base 16, obviously, is what this top abacus is used for. How about, guys, how many seconds in a minute? How many minutes in an hour? 60? Huh, where does that come from? Huh. How about ancient Babylonia? They used to have a base 60 system. So you'd have individual characters for 0 through 59, right? And then that would roll over to the next place value. Right? Got those. Wait, where's another? I had another picture on here. That's fine. Look at this guy from 1914. He's got his abacus. Right? Speaking of which, let me find here. Got this dude here. Found this video of this abacus bead. Oh yeah, got all these school kids like learn how to calculate. Right? In fact, some of them near the end here, they get so fast with this abacus and so good at it. Screen keeps freezing. It's been weird this year, right? I think this kid at some point starts doing calculations just in the air with his fingers. Yeah, there he is going right there. Let's see this again. Watch, oh, see him moving his thumb right there. Blah, 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 blah. So he's doing all that, just sliding beads around his mind. He's doing all these fancy calculations. So anyway, look for that. Thursday and Friday, I'll have you guys construct an abacus. I'll have you guys be taking square roots by the time you walk out this weekend. Things pace out right. All right, so that'll be fun. All right, but main thing for today is let's go through all these questions I pulled straight out of your book, all these word puzzles, like real applications of this stuff. Like where did you use this math? Right. And these are, by the way, in order in your book. So and I tried to pull something from about every chapter, like in order. So a machinist programs a laser cutting machine. Ooh, you guys think if you're using a 3D printer, there was some math that went into figure out like exactly how do you cut this or that. You need some equations for laser beams. Hey, laser beams. Ooh, what shape is a laser beam? That's a straight line. I bet you could model that with like a y equals mx plus b. In fact, here they are. One beam is programmed for y equals 0.5x minus 3.15. Now there would be units on those. I don't know if there's like millimeters or something. And the other is programmed to follow, 10x plus 5y is 63. Looks like they gave you two different forms of those graphs. Now, some of this might be a little bit of review from Algebra 1. Because this first equation, y equals 0.5x minus 3.15, what form is that in? That's in what form?
Slope-intercept?
Yeah, slope-intercept form. Yeah, slope-intercept. Versus this other one, 10x plus 5y is 63. That's in what form? Standard form. Yeah, standard form. Okay. So maybe there'd be a way to graph those equations and find the point that they intersect, where the laser's focused. Huh. Okay. Get that. Got it. Model high school band selling ride tickets for a school fair. On the first day, got 250 children's tickets and 150 adult tickets, sold for $550 total. On the second day, we got 180 children's tickets, 120 adult tickets, sold for $420. Okay. What is the price of each child ticket and each adult ticket? So one thing that I want you guys to get from this class is, having worked with math so much in the past or this year, maybe you'll be able to intuit or figure out like what you can solve. The fact that there is enough information embedded there that you can answer a question like that. Right? Like, how much does each ticket cost? Is there a way I can find out? Yeah, there's enough information there where there's definitely an answer to like that. Okay? How can you take this and turn maybe to more like an abstract algebra type equation and solve a system of equations? Okay. Chemistry. Miss Washington preparing hydrochloric acid solution. She will need 300 millimeters of 5% HCl for a class to use during a lab. Okay, so she needs exactly this much of this concentration. Okay, she has. Okay, so she goes back to her lab area, pulls off the shelf. Okay, 3.5% HCl. Okay, so that looks too dilute. That's not quite going to work, right? Oh, but there's also this. There's also 7% HCl. But that's too concentrated. So she has some that's a little bit too dilute, some that's a little bit too concentrated. Do you think in principle she could mix those together and get something that's kind of in the middle that's exactly what she needs, that 5%? Right? It's more than 3.5, it's less than 7. Huh. And one more factor here. She needs exactly this volume, 300 millimeters. So that's the question. How much of each solution should she use to mix together? So she has exactly 300 millimeters of exactly 5%. Huh. How can you make an equation out of that, solve that equation? She can run her chemistry demo. Miss Patel invested $825 in 2 stocks. At the time of her investment, stock A was valued at $12.41 and stock B was valued at $8.62. She purchased 79 shares. What's the system of equations to represent that scenario? How many shares did she buy? And how much did she invest in each of the 2 stocks? Kind of reminds me of that ticket question a couple slides back. Right? So there's enough information there. You can create equations and solve that. Okay. Ooh, these models. Some of these pictures, by the way, I just found on Google, so may not exactly match the premise, but if you look at the picture, you can get the idea where this is going. It looks like somebody throws a ball up in the air, right? Throws a ball straight up, right? Guys, if you trace this out, what shape does this make right here? Take a guess. Makes a what? I'm thinking a word that starts with the P. Parabola. Oh yeah, see a parabola right there. Right? Now, even if you threw a ball straight up in the air and you say want to make a graph of height as a function of time, so how high is the ball from the ground as a function of how much time it's been in the air, that would also make the same shape. It would also make a parabolic shape, right? Okay, Ben, kind of spoiling this a bit. So let's go read this question. From 4 feet above a swimming pool, Thomas throws a ball upward with a velocity of 32 feet per second. The height of the ball as a function of t seconds is this equation right here. So height is a function of time. So negative 16t squared plus 32t plus 4. Right? Now, the other main class I teach is physics, and there's definitely a connection here. So I might connect things to physics here and there. So in physics, I would definitely emphasize putting units on variables. So t is time is definitely in seconds. They spell that out. But it looks like, guys, what do you think h, this height, would be measured in? Feet. Because they give you a velocity in feet per second. Okay, so it kind of makes sense that height would have to be in feet. Versus my physics class, they use metric systems, so we try to stick to meters and so on, right? Right. But it'd be this equation right here. So you figure out exactly how high is the ball as a function of time, right? For time is greater than 0, so like right as he's releasing the ball and or equal to 0, so right as he's releasing the ball and afterward, find the maximum height reached by the ball and the time that this height is reached. Ooh, so how about this? I know I've run into a question before where somebody like throws a set of keys straight up in the air, and his friend is like up in an apartment building, like 3 stories up. They want to know like how fast do they have to throw the keys up, and at what time does the friend catch the keys, and how fast the keys moving, right? It's a really similar type question. You can model it with this equation, right? Now you guys said this was a parabola, right? How about this? What if I want to know exactly what time is the ball at any particular height? Like, what about this height right here, right? Now, if you wanted to solve that equation, I bet you guys could do that. And how would you solve it? You would need to apply the what? Quadratic formula, make a quadratic out of it, right? So, like, set this equal to some particular height, right? Oh, speaking of which, guys, out of the quadratic equation, you normally get how many solutions? Yeah, 2, right? You might get 0, you might get 1, but oftentimes you get 2. Because look at this, it looks like any particular height. There's actually 2 different times. Is that height? Yeah, 2 solutions that, again, would come out of the quadratic equation. Right. Except for its maximum height. Its maximum height, there would only be 1 time, only 1 solution. And anything above that, it's never going to reach. So there would be no solutions. Oh, look at that. Practical application of quadratic equations. Ooh, business models. Right. Now, before I read this premise up here, let's look at this graph, which again, I just found somewhere on Google and just slap this in here. Right. This is from economics, specifically microeconomics. Let's see if you guys can figure out what this is about. So let's look at these axes. We've got P versus Q. So since this is economics, what do you guys think P stands for in economics? Ooh, close. On a graph. Price. Yeah, I'm looking for price. Right? So this is a price axis right here. Price. What do you think Q stands for? Quantity. Yeah, so we've got price versus quantity, right? And we've got some curves. Tell you guys what these are. So this green curve is called marginal cost. That's the cost to produce 1 additional unit. So as you produce more, let's say I'm producing like these ink pens right here. So it looks like the first ink pen, there was some cost like per unit, right? And to make an additional ink pen, it looks like for a while it goes down a little bit, but then turns around and goes up for the main part of the graph, right? So it keeps it, right? That's really common in economics for a number of reasons. Yeah, let's go with this gold curve. This gold curve is called average total cost. So what's the cost per unit? If you take the total cost and divide by the total units that were made, right? So when you create the first unit, like the very first ink pen, did you have to build the entire factory that cost like $1 million just to make the first one? Yeah, so the average cost of the first one is like $1 million because you have to include the factory. That's like this point up here, right? But as you produce more and more and more ink pens, does the cost per unit come down? Yeah, right. But not forever. After a while, it actually bends back up. Right? Average variable cost is also cost per unit. It just, you subtract out the factory itself. It also looks like this, right? And then the orange curve is average fixed cost, which is really just looking at the factory itself. So if you build the factory and make 1 pen, the average cost is a lot, right? But if you make like 1 billion pens, then you divide the factory by 1 billion and, ooh, guys, is this asymptotically approaching 0? Huh, yeah, right. Now that I'm looking at it, just realized this earlier today. There's a curve that is not on here that would have been helpful, which is revenue, something to do with revenue. But it depends what kind of uh, industry you have. But sometimes the revenue is just like a flat line across for well, if it's like a competitive market kind of thing, right? Anyway, let's go read this this right here. So an accountant determines. So maybe you're an accountant, maybe you are an entrepreneur, a business leader, economist. Right? This could all tie into the daily cost to operate an airbag factory. All right, we're making some airbags. Can be modeled by the function cost as a function of quantity. Isn't that what C as a function of X would be? Right. 3x squared minus 10x plus 200. Right. So however many airbags, you guys plug it in here. Like, guys, if you make 0 airbags, guys, if you plug in 0 for X, 0 airbags, what does the cost come out to? What's 0 squared times 3? That'd be 0. Minus 10 times 0 is 0. Plus 200 is 200. That'd be 200. Ooh, do you guys think just to build the airbag factory, it costs 200, oh, I don't know, $1,000 or whatever it was, 200 units of money? Yeah, that's what the 200 represents, right? Or I think so. That would make sense, right? Right? Logically? Right. And then every airbag that you create after that, if you create like 5 airbags, that you can put like 5 for the X there. Oh, no, they're in thousands or hundreds of thousands. So 500,000, put 5 in it, right? Where X is the number of airbags sold in hundreds of thousands. So if you make 500,000 airbags, plug in 5 for X kind of deal, right? She also determines the factory's revenue can be modeled by, this equation, negative 2x squared plus 100x plus 50. Here's what basic shape would that be? If you see x squared, that's always creates a what? Starts with a P. Parabola. And if it's negative, it's a parabola oriented which way? Yeah, upside down. Okay, I bet this is an upside down parabola. So maybe some upside down parabola I could put here to represent revenue. Where X is the number of airbags, again, sold in hundreds of thousands. What is the range of number of airbags produced a day to ensure the company maintains a profit? Ooh, maintains a profit. All right. So if you don't create a lot of airbags, then that factory is pretty expensive. You're sitting in the red. If you create too many airbags, looks like those cost curves are going up. It's probably also not good. But maybe there's some optimal number of airbags for, okay, if we make between like this many airbags, we are running a profit. Right? Right, probably your goal is to create a maximum profit. So maybe there's some exact number of airbags that you know you'd have to create because you have equations that you can attach to any of these curves, right? Now, if you take microeconomics, you can find like exactly what's the price point, what's the quantity to create to maximize the profits for your airbag factory. Oh yeah. Aha. Yeah. That's a great question. So, Eric, I wasn't gonna do that, but let's dig into it a little bit more. What do you guys think profit is? Profit could be what minus what?
How much cost to
Rev.
profit?
Cost minus rev.
That's what I'm looking for there. Yeah, the difference between revenue and cost. Yeah. So if you do revenue minus cost, there's your profit, right? So we sold this many, great, we made $1 million. But it took $1 million to make it in the first place. That would be a profit of 0, right? Because $1 million minus $1 million would be 0. Like that. Yeah. Right. So I bet if you set revenue equal to cost, that you could determine like those exact points where it's like, okay, well, we don't want to make less than this or more than this because be somewhere in between. Yeah. Okay. Ooh, use models. A canister has the shape of a cylinder with the spherical caps on each end. I think they're talking about like a capsule pill, right? Maybe you could put like some medication or herbs or something in here like that, right? And they give you a volume in cubic millimeters. Yeah, so a real small little capsule, right? Can be modeled by the function. Oh, okay, so volume is a function of x, where x, by the way, is the radius. So x is the radius. So volume is a function of radius, if you like. It could be this expression. So got a pi in here. It looks like got 2 terms added together. Got an x cubed here, an x squared here, right? Where x represents the radius in millimeters. And the canister is x plus 3 millimeters wide. Okay, so now we're introducing another constraint, right? So no, the radius is x. We're going to make it how long? Okay, x plus 3. Well, from there to there, not including the ends, it looks like, right? Says use a graphing calculator to sketch the model that represents the volume of the canister, include axes as labels. Right. Now in this class, in all my years of teaching, I've only ever really used a scientific. That's all I've ever needed. You guys have laptops as of yesterday. So you guys know a site called Desmos? Yeah, I'll probably have you guys pull out laptops for Desmos, well, a number of days, but we'll see. If you have your own graphing calculator, you can use that too, right? So yeah, we're gonna make a graph to represent this scenario, right? What's the domain of the model? Why could there be restrictions? Like how small or large could this particular capsule pill be? Well, I was thinking of a capsule shape that kind of reminded me of a submarine design too, right? So hey, how about this? Suppose you're working for Lockheed Martin one day. You got some competitor over at Northrop Grumman, and the government wants you to build submarines, and they want something that works and has all these functions, and it's going to be good. It's going to last 50 years, but they also need the lowest cost, right? So now we're in the bidding war and got these two companies, right? And you need to design the submarine, and we need to design it so it does all the cool stuff and it's good for 50 years and stuff, right? But maybe with the least materials, so it has the least cost, right? And so you start breaking out these equations and start solving stuff. Luciano has a square garden. A new garden will have the same width and a length that's 3 feet more than twice the width of the original garden. Okay, so we got the square, got this rectangle. Define a variable and label each side of the diagrams with an expression for length. What is the write a ratio to represent the percent increase in area of the garden. Use polynomial division to simplify the expression. Use your expression part B to determine the percent increase in area if the original garden was 12 foot square. Check your answer. Ooh, so it's not even until question C that they tag enough specific information where you can get a very specific scenario. Looks like questions A and B are be generically applied to a whole class of situations, right? Ooh, you know what else this kind of reminds me of? Here, I'm going to throw a calculus question at you guys, which I'm not going to so much see in this class because not but maybe thinking ahead a couple of years. A lot of you guys might take calculus one day. What this reminds me of is, suppose you have a budget to buy a certain amount of fencing, and what does it say at the bottom? 12-foot square. What's 12 times 4? Is that 48 feet? 48 feet of fencing? Right. Maybe that's your budget constraint. I have enough money to buy 48 feet of fencing, and that's all I can buy. Then, right. What shape garden would you have to create to maximize the area of your garden? So if you want to maximize the crops that are growing in it, right? What shape would that be? Right. Okay, suppose you have some kind of rectangle, right? So I can have a little skinny rectangle. I can have a wider rectangle. But remember, keep in mind, I'm constrained to like 48 feet of fencing, right? If the block is, I guess it could be a square, right? Which shape do you think would? Here, I'll sketch it out. Let me switch my camera over here. I'll sketch this out a little bit. This. Suppose I have 48 feet of fencing. I could create this looking garden. I could narrow it down, make it look more like this. Could also be 48 feet with fencing. I can make it look like a square. Maybe those are all probably pretty close. They're all like the same perimeter, pretty close. Right? Which one of those do you think would have the largest area? You think that square right there? How many of you guys think the square? Yeah, right. Turns out you need calculus to prove that. But yeah, it is a bit. How about this? What if you're not constrained to a rectangle shape? Is there a different shape you think you can get even more area than a square? Circle. Yeah. If you take your fencing material and put it into a circle, that's even better than a square. Yeah. So that one day, got here. Oh, okay, we got another garden situation, 12 by 16, surrounded by a border of mulch that's uniform width. We're going to call it X, and give you a nice convenient picture right there. The maximum area for the garden plus border is 285 square feet. Write a polynomial to represent the situation. Going to be a system of equations out of this. What are the dimensions of the garden plus border? Ooh. Packaging. Juice manufacturer creating cylindrical packaging. Give you guys a cylinder right here. Oh, look at that. Got a cylinder full of pineapple juice. The height of the cylinder is to be 3 inches longer than the radius of the can. The cylinder is to have a volume of 628 cubic inches. Use 3.14 for pi. Right, so, hey, maybe you're making pineapple juice. Okay, we're going to have this signed can. There's so much juice we want to put in here. We have the nutrition labels ready to go. We want that particular volume. But, the grocery stores that we're going to ship this to, they have a particular design shelf space. And so, okay, so we better have this radius. Okay, so it's got to have this height. So, right. Yeah, and we've got to solve that. We need to turn this into equations, polynomial equations. Got to solve the system of equation. Right. And what would exactly be the radius and height so that we can fit in the juice we need and it also fits on the grocery store shelf. Space. Technology for a rocket that will safely return to Earth after refueling and reuse is being developed. 3 sections of the booster that power the flight and the payload are cylindrical, and the total volume of about 234 pi cubic meters. So if you like in your calculator, 234 times 3.14, so many cubic meters. The second stage of the booster is X meters tall. Right, so okay, so we got these stages here. Looks like we know how tall this one has to be. The interstage section is X plus 3 meters tall. The first stage is 5X plus 6.5 meters tall. The radius of the booster is X minus 5 meters. Okay, so we all have all these design parameters. Maybe there's different sections of teams of engineers that are working on building this thing. Okay, we need some particular volume in here so we know how much oxygen to put in and how many astronauts we can fit in here and everything we can take up from space. Okay, we need some rocket fuel. We need certain design parameter. What's going to fit on the launch pad, and they come up with this whole system of equations. Looks like all these equations would be related to each other through X. Right, right, and solve a system that could represent the volume of the booster. There you go. Right, so we can ultimately maybe figure out how much oxygen do we need to supply and so on. Right. What are the dimensions of the first stage section of the booster? Okay, so we figure out exactly the dimensions. Right, the information's lying around. Right, they hand it to you. You did math, and yeah, figure out how to design a rocket. Temperature formula for converting temperature in degrees from Fahrenheit to Celsius, and they give you this expression right here. So temperature is a function of well, starting from degrees Fahrenheit, could be X, I think. Okay, got 5/9 times X minus 32. Find the inverse and describe its meaning. Okay. I gave you guys some scales side by side. Here's a Fahrenheit scale. Here's a Celsius scale. So if you went outside today, and maybe it's like 70 degrees outside, 80 degrees, whatever it is, right? But there's something implied in what I just said. Because if I say it's 80 degrees outside, I really mean it's 80 degrees what? Fahrenheit. Okay. Then say you take a trip to England. Say, oh, it's a jolly 21 degrees outside. 21 degrees. And oh, wait. That's Celsius. You convert that back to American. Huh? How can I do that? Yeah, you know that one. Yeah, so 1.8 or 9 fifths times that temperature in Celsius, then at 32. Yeah, which turns out actually is exactly the answer to this question. I wasn't going to be answering questions, but yeah, head of the game there. That's it. The inverse describes meaning. Okay. So yeah, so you could. How many of you guys have ever been outside of the States? Who's ever been outside the States? Yeah. Right, so if you got a weather report, you can convert that back into Fahrenheit. Right? Or if you were somebody visiting the States, let's say you grew up in England and visiting the States, yeah, maybe you'd want this exact expression right here to convert an American Fahrenheit temperature back into Celsius. It's the other way. How about this? Suppose you don't have a calculator on hand and you just need to do some mental math. Like, okay, the guy said it's something like a jolly 21 degrees outside and I need that in Fahrenheit. Can I do a quick mental calculation and get a pretty close idea? So let's look at this number right here, 5/9. Guys, 5/9 is really close to what much easier fraction to work with. 5/9 is really close to a. All right, so I got a picture of this. I gave you guys this page a couple days back. I gave you guys a fraction table. So numerator, denominator. Let's do this 5 over this 9. 5/9. Okay. Suppose you have a pizza. These could all be pizzas. Look at all these pizzas. Ooh, all these pizzas. And let's say you slice it into 9 slices. 9 slices. Right. Well, you slice it into 9 parts. Right? And you have 5 out of 9 parts. What does that look like? So 5 out of 9. Is that point? That one right there? Is that 5/9? 5/9? Ooh. It looks really close to what? 1/2. It's a little over half, isn't it? A little over half. Aha. Right. So back here then. Boink. Right. Yeah, I bet you could round that to about 1/2. Ooh, 32. Is that kind of close to 30 about? Yeah. You could go both ways too. So you said 1.8x plus 32. Yeah. So you could round that to 2 times x and then plus 30. Mind you, pretty close. Okay. Bianca invests $5,000 in an account that pays 5% annual interest. Ooh. So the first year you earn 5% of that, but the year after that, you earn 5% on like everything that's accumulated. Right? It takes off into a ooh. Because if you're earning an additional 5%, then 5% on top of that 5%, and then the next year 5% on top of everything that's accumulated. That's going to create a what kind of growth curve? Starts with an E. Exponential. Yeah, it's exponential growth. Exponential growth curves are wild because they start off looking kind of flat. It's like, okay, I only got a few dollars extra, right? But they take off like almost vertical, looking real after some time, right? Write a function that represents the value of Bianca's account y after x years. Okay, so x years have passed. What's the amount account y? After how many years will her account be $25,000? Ooh, so let's say she starts with $5,000. She wants to get up to 5 times as much, right? How much time does it take for her money to quintuple at this particular interest rate? Solve that. Okay. Moore's law. Gordon Moore, the co-founder of Intel, suggested that the number of transistors on a square inch of integrated circuit in a computer chip would double every 18 months. Hey, does that also sound like exponential growth? Right? Like double, double, double? Let's do some doubling. What if you start with 1 of something and you double it? Now you have 2. Double that. Now you have 4. Double that. Now you have 8. And then, ooh, you can keep going with that, right? Keep going, right? All right, so yeah, this is called Moore's laws. How many transistors can you fit economically on a computer chip? Yeah, so again, I pulled this off Google. Actually, I do have this one also in my bay right outside my window. So if you happen to see this one hanging up out there, right? So these are, every dot here is a commercially released computer chip. And look along the x-axis here. These are years. So it starts at 1970, and here I got 1980, 1990, 2000, 2010, and 2020 right there, right? Okay, now if you stand back and look at it, say, okay, well, it looks kind of linear. Do you think you could put your ruler down and just straight line of best fit through that? Yeah. But here's the catch, is that the vertical axis on this graph is not scaled linearly. Guys, look at this. 1,000, 10,000, 100,000, a million, 10 million. Is that scaled by like factors of 10? Factors of 1,000, right? Yeah, so that is actually an exponential curve. Right. And the sets of axes are called, that's a semi-log axis system. Semi, because only the vertical axis is scaled like logarithmically or exponentially, right? If you graph this linear versus linear, like if you actually put the transistors like 1, 2, 3, 4, 5, okay, this curve would look really wacky. It start off looking like almost flat, and then it would take off like almost vertical looking, and it'd be really hard to make sense of that. But if you do a semi-log graph, now you can make sense of this. Again, yeah, every one of these blue dots is a chip that was released commercially. Okay, so back to this question here. Assuming Moore's law holds true, how many times as many transistors would you expect on a square inch in year 6? All right, so many years out, which can we expect, right? The real, okay. A real world application of this is since software designers, computer manufacturers, they all know that this is true, or it's been true a long time. I mean, at some point you ran into some physics limits, I guess, but so if you go back to the 1990s, 2000s, the software designers say if you want to design the next operating system, right? So we're gonna have Windows XP and then Windows ME, Windows 2000 and Windows 10, right? So every time you design a new operating system, they're actually designing it for computers that don't exist yet. Right? Okay, well, what will computers be able to do like 1 or 2 years down the road when this is eventually able to be commercially released? Yeah, because they know this Moore's law. Do that calculation. Right? Biotechnology, the pH of a substance. Ooh, pH. We're talking about, let's say it, right? Can be represented by the equation y equals negative log of H plus, where H plus is the concentration of hydrogen ions in the substance. Right? How many guys have, or like right now, are in a chemistry class? Who's in a chemistry class? Yeah, right. Who took chemistry last year? Did they take chemistry last year? Okay. So I got some of each on both of those. All right, so yeah, so this is a chemistry question. Right, if something's acidic versus basic, maybe you got different household cleaners, right? But if something has a pH, here's a pH scale. Because does pH normally go from what, 0 to 14 normally, right? Those numbers are actually powers of 10. So if you have a pH of 5, that's actually 10 to the negative 5. If it's 11, it's 10 to the negative 11. And that's, again, a concentration of hydronium ions, this H plus, right? Could you have a pH of 15? Could that be a thing? Could you have 10 to the negative 15? Yeah, you could. It would just be so basic at that point. It's really rare to happen, but it could happen. Right? Could you have a pH of -1? Could that be a thing? Yeah, because it could be a power of 10. And since these are negated, it'd be 10 to the -1 would be 10 to the power 1, which would be like crazy acidic. It'd probably like burn through almost anything, right? Ooh, how about this? Let's do a little bit of help you guys not kill yourself one day. What if you have some household cleaners? You have one that's a strong acid and one that's a strong base, like a bleach base might be like really basic, right? And you have some like vinegar, like really strong acid, right? Like this sink is so dirty, man. I really need to clean this sink. You want to mix together an acid and base? Like this is gonna be super clean. You want to do that? No, because if that base, like Clorox, has chlorine in it, there's a chemical reaction between the acid and the base. Guess what you're about to be breathing in? Yeah, chlorine gas. Yeah. Yeah, so not so good. So don't mix acid in the base, right? Okay. Well, things to know. The value of hydronium ions usually varies between, oh, look at that, 10 to the -14 and 1. That'd be a pH of 14 versus a pH of 0. And 0 is really 10 to the power of 0, right? Because what is 10 to the power of 0? 1. Hey, that's what this is right here. 1 mole. It's like a concentration. For example, lemon juice is on the acidic side with, 10 to the -2 is the actual concentration of hydronium ions. But we'll call that a pH of 2, because 10 to the -2, call it pH of 2. That's extremely acidic, is lemon juice. Household bleach has 10 to the -13, so we'll call that a pH of 13. That's opposite ends of that scale, 2 versus 13. Guys, where is water on this graph? Water is what? Is a 7. Yeah, water is a 7. That's like, we'll call it neutral. It's like neutral right in the. All right, so they're going to have you guys graph this function, list constraints on domain and range, and what would that even mean? State the intercepts, intervals where the function could be increasing, decreasing, positive, negative in behavior, asymptotes of the graph, interpret them in the context of the situation. Again, because a graph just out of context might look abstract, but all these graphs mean things, right? All right, you connect that back. Right here. All right. Apple juice has a pH of 3. So as a concentration, I might call that 10 to the -3 moles of H plus, right? 10 to the -3, right? Milk has a pH of 6. How many times more acidic is apple juice than milk? Actually, we'll do this here because last class they were curious about this one. We solved this a little bit. Right. You guys see a difference of 3, like 6 versus 3? Right. But again, you guys know that's actually a power of 10, right? So if you have a power of 10 that's different by 3, let's do some numbers. You guys told me 10 to the 0 was 1, right? 10 to the 0 is 1. What is 10 to the power of 3? 1,000. Yeah, 1,000. Because it's 10 times 10 times 10. Power of 3 means you're multiplying it that many times. 10 times 10 times 10. Right? So if you have a difference of power of 3, which is what these pH numbers are, 3 versus 6, that's the difference there. Right? That's how many times is concentrated? About 1,000. Yeah. 1,000. Biology. There are initially 1,000 bacteria in a culture. I have an agar dish here. So if you had some sample, right, you put a little sample of bacteria there, it's got some nutrition, like some food you can eat, starts to grow. The number of bacteria doubles each hour. Oop, that sounds exponential, doesn't it? Right? The number of bacteria after T hours is given by this equation right here. Right. Now it'll start off like that. It'll start off exponential. Now realistically, there's more to this question that could be because there's only so much nutrition on that agar dish. So eventually it levels out. So that'll be like a logistic curve, but they're not even quite there yet. Right? How long will it take the culture to increase to 50,000 bacteria? Right? So I want n to be 50,000. Oh, how do I solve for that t? It's an exponent. How do I get numbers out of exponents? It's a way to do it. By the way, do you guys know how to get numbers out of exponents? How to solve for numbers that are in exponents? Someday I'll teach you guys about logarithms. Right. Oh, here's another logarithm question. Right. Logarithms are the opposite of exponents. Equation loudness in decibels. Right. You guys ever heard like how loud is something is expressed in decibels? Right. Now it turns out that that's also a logarithmic scale. Right. So L loudness equals 10 log R, where R is the relative intensity of the sound. Yeah, there's two ways to measure like directly how loud is something. You can do intensity. You can also do pressure. Guys, the sound of pressure wave, as in talking, is the air vibrating, and that's vibrating your eardrum, and that's how you're hearing me right now. Yeah, so intensity, pressure, different ways. Compared to the minimum threshold of hearing, which would be like 0 decibels. Now, 0 decibels does not actually mean zero sound. It's actually a power of 10, just like pH was. So it's like 10 to the power 0. Like you can barely hear somebody's whispering, right? One city's emergency weather siren is 138 decibels. How many times greater is that than the minimum threshold of hearing, right? Again, if we're talking about in terms of intensity, right? Not the decibel number itself, intensity. Right? Here, I'll tell you guys, right now as I'm speaking, I'm probably speaking approximately 60 decibels. Let's call it 60 decibels. It's usually just talking, right? What if I talked twice as loud? Or what if there were two of me and we're both talking? I doubled my volume. What happens to the number of decibels? Do you think it goes from 60 to 120? Turns out it doesn't. It only goes from 60 to like 63 because it's like a power of I think a power of 2, something like that, right? So 60 to 63 is actually doubling. Right? All right, cabin rental. Ooh, look at this cool cabin right here. So a group of friends. So you and your friends want to rent this cabin at the Red Pine Ski Lodge. The cabin costs $750 to rent for the weekend. Let X be the number of friends who are sharing the cost, and Y be the cost per person. We're trying to figure out a function representing the average cost per person to rent the cabin. Analyze the key features in the graph. Gonna make a graph out of that. So you and your friends want to get together in that cabin. You want to rent it. You know the price of the cabin itself, but we got to figure out how much is each person going to chip in. It really depends on how many friends are going to show up. Okay, well, I have like 10 or 12 friends I want to invite, but not everybody's able to show up. I know for sure like 2 or 3 can, and I've got like 7 or 8 that are on the maybe list, right? So how much does everybody have to chip in? Well, the best I can do right now is craft an equation to represent that. What does that equation look like? How does it graph? And then what do all these features of that graph represent? Ooh, right. Hey guys, what if you had a bunch of friends? Like the more and more friends that pitch in, what happens to the cost per person? Goes down. Did we talk about what kind of relationship is that called? If one variable increases, another variable decreases, that's called a what relationship? No, we hadn't talked about that. Huh? Wait, somebody say it. Starts with an I. Okay. I think some of these coming up. Yeah. It's called an inverse relationship. Inverse relationship, right? The more friends, the less cost per person. One goes up, the other goes down. All right. Electricity. Ooh, here's a good physics one. Total resistance of a piece of wire varies directly with its length. Right, so pause right there because that means something specific. If something varies directly, that means if you double one variable, another variable also doubles. Do you think if a wire is twice as long, it's also twice the resistance from end to end? Right? What if you have a wire that's a mile long? What if you have a wire that's 2 miles long? Is that twice the resistance for twice the length? Yeah, that's called a direct relationship. Okay. Great. And look at this word, inversely. Inversely, with the cross-sectional area. That means this. What if you have a little skinny wire versus a big fat wire? Little skinny wire, big fat wire. Which do you think has more resistance? The little skinny wire or the big fat wire? How many of you guys think the skinny wire has more resistance? Little skinny has more resistance. How many of you guys think? Who thinks the fat one has more resistance? Right? Yeah, it turns out the little skinny wire has more resistance. Right? So as you decrease the cross-sectional area, the resistance increases. Right? What do you think is easier to drink through or harder to drink through? A little skinny straw, like a little mixer straw, or like a big wide straw? Yeah, a little skinny one's really hard to draw liquid through. Big fat straw, that one's easier, right? There's not as much resistance, right? Okay, so I'll throw some numbers at it. A piece of copper wire, which by the way, this copper could also be part of an equation too, because do you guys think that if you have 2 otherwise identical wires, but one's copper and one's aluminum, do you think those transmit electricity a little bit different too? Yeah, materials, right? We've got 3 meters long and 2 millimeters diameter. Got this total resistance. What about another piece of wire that's a different length and a different diameter? You have to relate that to cross-sectional area and then resistance. What's that relationship? There is enough info there, you can solve that. We got plant size is directly related to the water that the plant has access to. So if you double the water, you double the plant size. And inversely proportional to the bacteria. So if there's more bacteria, there's less plant growth. Right, they throw some numbers at you. Can you solve that equation? Ooh, pressure. Let's look at this one. We got balloons. The volume of a gas varies directly with temperature and inversely with pressure. This is called the ideal gas law. Let's think about this. Guys, suppose there's a fly flying around. You guys see a little pet fly? Here's my pet fly. Call him Philip. Okay, Philip the fly. And if you heat up the balloon, guys, heat up the balloon. What does the balloon do in terms of its volume? It expands. If it's twice as hot in terms of Kelvin, twice as hot, you think it's also twice as big? Yeah, that's called a direct relationship. Yeah. What if you start squeezing on the side of the balloon? Squeeze on the side of the balloon. What happens to the volume? It gets what? Gets smaller? Yeah, it gets less, gets smaller. What about Philip the fly inside? What does that fly feel like is happening to the pressure? As you squeeze the balloon smaller, the pressure gets what? Increases. The smaller the volume, the larger the pressure. Huh. They throw some numbers. Can you solve that? All right. Let's do it. All right, last one. Drama club. I got a Venn diagram. Got these students in Act 1, these students in Act 2. If we choose someone at random, what's the probability that they were in only one act? Right there. All right. That's all we got time for. Good life. Guys, like. Tomorrow we'll be doing abacus. So tomorrow is abacus day. Have you guys construct that, and again, we're eventually working towards most of the time saying, have you guys be taking some square root sine beads in time.